So, in today's session, we are going to learn about a few important continuous random variables. We first begin with the uniform distribution. Now, when we look at a uniform distribution, again this is the important thing which we need to understand as to what is a uniform distribution. So, let us go back and understand what is a uniform distribution. So, if you remember, if this is my x, this is going to be my PDF f of x. So, we introduced the concept of a probability density function in the last class, and we said that if f of x is a probability, if x is a random variable which takes values in a particular range, then over that range my f of x, in other words, if x belongs to a interval a b, we said that a to b f of x dx should be equal to 1 and f of x should be non-negative in that particular interval. This is how we defined a PDF. So, now this is a very important property that the probability of x belonging to that interval is going to be equal to 1 and hence integral a to b f of x dx should be equal to 1. This is what we discussed last time. So, now what is a uniform distribution? As the name suggests, if I have any interval a to b, then f of x is uniformly distributed. In the other sense, f of x takes a constant value throughout this interval. So, I can say that f of x is a constant, some constant k for a is less than or equal to x is less than or equal to b. Now, remember again in the last session we said that x taking a particular value, if x is a continuous random variable, does not make sense because it is continuous. So, f of x, if a is less than x is less than b, is equivalent to a is less than or equal to x is less than or equal to b. Hence, some books refer to a uniform random variable on a closed interval. Some books refer to it as an open interval. We are going to assume that both of them mean the same. So, what does this mean that uniformly distributed? Uniformly distributed means that f of x has constant density in this interval a to b. So, now what is this constant density? Now, if it is a constant density and if f of x has to be a probability density function, then I know a to b f of x dx, which is the same as this constant times a to b dx. Constant comes out, this is a to b dx, which is nothing but k into b minus a. I know if this is a PDF, I know this should be equal to 1, which gives me the constant is 1 by b minus a. So, what have we achieved here is f of x is between a and b and this is x. So, if x is a uniformly distributed random variable in an interval a to b, then the probability density function we have obtained the constant equal to 1 by b minus a. Hence, the probability density function is 1 divided by b minus a for a is less than x is less than b. So, this point is 1 by b minus a and it is 0 otherwise for any real value of a and b. So, let us look at a few examples. Now, suppose my a is 2 and b is 4, I know b minus a is 2, which gives 1 by b minus a is 1 by 2, which is a 0.5. So, you can see that f of x is a constant with f of, so if this is my f of x, it is taking a constant value which is equal to 0.5 for any value of x between 2 and 4. Let us Look, another case where a is minus 2 and b is 2. So, my b minus a is 2 minus of minus 2, which is 4, which gives my 1 by b minus a is 1 by 4, which is 0.25. So, you can see in the interval minus 2 to 2, f of x is taking the value 0.25, and this is a constant in the interval. So, in summary, if I have x is a uniformly distributed random variable in an interval a to b, again I am not making a distinction, I am going to represent it as open interval a to b. Some books represent it as closed interval a to b. I have a probability density function which takes the value 1 over b minus a or 1 by b minus a for x lying between a and b and 0 otherwise. So, it is taking the value 0 outside the interval, and within the interval it is taking the value 1 by b minus a. A special case of the uniform distribution is when a takes the value 0 and b takes the value 1, that is minimum is 0 and maximum is 1, and this is referred to as a standard uniform distribution. I repeat, a special case of a uniform distribution where the minimum value is 0 and maximum value is 1, okay, is referred to as a standard uniform distribution. And for that, so with the density, it is again going to be 1 by b minus a, b equal to 1 and a equal to 1, which is equal to 1. So, my density is 1 for x lying between 0 and 1, 0 otherwise. So, the density function will take the value 1 in the interval 0 to 1 and it is 0 otherwise. Now, we also can confirm that the area under the density function is nothing but minus 2 to 2 with 0.5, and you can see that is 1 by 4 into 4, which is equal to 1. Here it is going to be 2 into 0.1 by 2, which is equal to 1. And in the case of the standard uniform, this is 1, this is 1. So, the area integral f of x dx is equal to 1, all of it, hence verifying that this f of x or the PDF is indeed a probability density function. So, now we can verify for all of that this is a probability density function. This standard uniform distribution, it plays an extremely important role in random variate generation, which you are going to come across in your advanced courses, especially when you are going to simulate random numbers. This is about the probability density function of a uniform distribution and a standard uniform distribution. Now, what is the cumulative distribution of a uniform distribution? Recall, the cumulative distribution function or f of x was probability of x is less than or equal to x. Again, I know that this, if I am given a to b, I have, this is my probability density function. It takes the value, so it is taking a value 0 till it hits this f of x is going to take a value, and it is 0 elsewhere, and it is going to be f of x here. This is my probability density function. So, for x is less than a, so whenever x is less than a, my integral is going to be minus infinity to a f of x dx. I also know f of x takes the value 0 outside this interval. So, this is going to be 0, hence f of x is or f probability x is less than or equal to x for x less than a, f of x is going to take the value 0. Okay. Now, if x is equal to a point which is between a and b, suppose x is here. Okay. Now, for this point, my f of x is going to be minus infinity to x, f of x dx, which is going to be minus infinity to a, f of x dx, plus a to x, f of x dx. Now, I know that f of x takes the value 0 which for x is less than a. So, this will contribute a value of 0 and this is going to be a to x, f of x dx. So, for x lying between a and b, I have probability x is less than or equal to x is a to x, f of x dx. Now, x is lying between a and b. I know f of x when it is lying between a and b is 1 by b minus a. So, I have a to x into 1 by b minus a times dx. Now, this 1 by b minus a is a constant. So, what I can do is this 1 by b minus a can be taken outside and this becomes a to x dx, which I know is nothing but x minus a by b minus a. Hence, I have f of x is x minus a by b minus a for x in the interval a to b. Now, what happens for x is here. So, at x equal to b, I know f of x equal to 1. So, for any x greater than b, f of x is going to remain to be 1 because I know a cumulative distribution function is a probability and that lies between 0 and 1. Hence, the cumulative distribution function of my uniform distribution is given by the following, which takes the value 0 till it hits a. Between a and b, it would be a straight line because I can write this x minus a by b minus a as minus a divided by b minus a plus 1 by b minus a into x. So, I get f of x is, I can recognize that this is some constant plus a slope into x. So, this is a straight line with slope 1 by b minus ax and beyond this it is going to remain at 1. So, the CDF or the cumulative distribution function of a uniform distribution would be 0 till it is at A, it would be 1 beyond B and between A and B it is going to be an equation of a straight line with slope 1 by B minus A. So, again going back to our examples where A was 2 and B was 4, I can see that for this example B minus A is 2. So, the slope is going to be half, which is 1 by B minus A. For x less than 2, f of x was 0. For x greater than 4, f of x is going to continue to be 1, and between 2 and 4 we can see that it is a straight line with slope half. So, it is always the slope of the line between B and A is half. So, if you go to this example of a standard uniform, we know that f of x is equal to 1 for 0 is less than or equal to x or less than x is less than 1. So, my f of x is again 0 for x less than 0. So, x minus a by b minus a is the same as x minus 0 by 1 minus 0. So, f of x takes the value x for 0 is less than x is less than 1, and that is what we have here, and f of x takes the value 1 for x greater or equal to 1, and you can see that this is what for x less than 0 it is 0, for x greater than 1 it is 1, and between x lying between 0 and 1 f of x takes the value x. So, f of x takes the value x. So, this is about the cumulative distribution function of a uniform and a standard uniform distribution. Now, we will look at the important properties of a uniform distribution. Recall, whenever we are talking about a random variable, we always wanted to define the random variable, give the probability distribution function of the random variable, come up with a cumulative distribution function of the random variable, and look at the expectation and variance of these random variables. So, we are going to look now at the expectation. So, we are going to look now at the expectation and variance of the uniform random variable, which is uniformly distributed over an interval a to b. We all know that expectation of a random variable with a PDF f of x is over the range. So, the range here of definition is a to b, x into f of x dx. So, I have a to b, expectation of my x is going to be x into f of x is 1 by b minus a into dx. So, this is 1 by b minus a is a constant, a to b, x into dx, which I can say is 1 by b minus a. This is going to be x square a to b, which by 2, which is going to be b square minus a square by 2 into 1 by b minus a, which I am going to get is b plus a by 2. So, the expectation of a random variable which is uniformly distributed over a and b is a plus b by 2. So, we can see that it is a plus b by 2. Now, let us look at the variance. To compute the variance, we use the computational formula, which is expectation of x square minus expectation of x whole square. Now, let us compute expectation of x square, that is going to be a to b x square f of x dx, which is going to be a to b x square into 1 by b minus a dx, because f of a x is 1 by b minus a. Again 1 by b minus a is a constant, a to b x square dx, which is going to be 1 by b minus a into x cube by 3 a to b. So, I get a b cube minus a cube by 3 into 1 by b minus a, which I know is b square plus ab into b minus a, and I get expectation of x square is b square plus ab by 3. Now, expectation of x we have already seen is b plus a by 2, which would give me expectation of x whole square is b square plus a square plus 2ab by 4. Hence, my variance of x is b square plus ab by 3 minus b square plus a square plus 2ab by 4. Applying x variance of x is expectation of x square minus expectation of x whole square. This is what we have been applying throughout, and here I can see that I get a 4b square minus 3b square, which is a b square, 4a square minus 3a square, which is a square, 4ab minus 6ab, which is a minus 2ab by 12, which gives me b minus a whole square by 12. So, we can see that the x variance of x is b minus a whole square by